Tonight, we're going to explore one of the strangest objects in the universe. Something that exists in a place that shouldn't be possible. It's not a planet. It's not a star. It's something caught in between. A brown dwarf. You've probably heard the term failed star before, and that label is everywhere. But here's what almost nobody explains. A brown dwarf didn't fail at anything. It never had a chance. There's a physical threshold, a line drawn by the laws of physics themselves, and brown dwarfs simply never crossed it. What makes this fascinating is how close they came. They formed the same way stars do. They collapsed from the same clouds of gas, but something stopped them. And what stopped them reveals one of the most important boundaries in all of astrophysics. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that seems obvious but is actually far more subtle than most people realize. What is a star? You probably think you know the answer. A star is a big glowing ball of gas in space. It's bright, it's hot, it shines. And that's true. But it barely scratches the surface, because the real question isn't what a star looks like. The real question is what makes a star shine. And the answer to that question is everything. It's the key to understanding why some objects become stars and others don't. It's the key to understanding brown dwarfs, and it starts with gravity. Gravity is the most familiar force in the universe. You feel it right now, pulling you into your chair, keeping your feet on the ground, holding the atmosphere against the planet. Gravity is what keeps the moon orbiting Earth and Earth orbiting the sun. It's what holds galaxies together across hundreds of thousands of light years. But gravity does something else. Something that's crucial for understanding stars. Gravity pulls things together. And when gravity pulls enough gas together in one place, something extraordinary happens. Space is not completely empty. Even in the vast stretches between stars, there are clouds of gas and dust floating through the galaxy. These clouds are called molecular clouds, and they're made mostly of hydrogen, the simplest and most abundant element in the universe. Hydrogen makes up about 75% of all the normal matter in the cosmos. Helium makes up most of the rest, about 24%. Everything else, every other element on the periodic table, carbon, oxygen, iron, gold, all of it combined accounts for less than 2%. These molecular clouds are enormous. Some stretch across hundreds of light years. They contain enough mass to form thousands or even millions of stars. But they're also incredibly thin by earthly standards. Even the densest parts of a molecular cloud are far more empty than the best vacuum we can create in a laboratory on Earth. The particles are so spread out that you'd encounter maybe a few hundred or a few thousand molecules per cubic centimeter. The air you're breathing right now contains about 25 quintillion molecules per cubic centimeter. A molecular cloud is trillions of times less dense than the air in your room. And yet, these thin clouds of gas are where every star in the universe was born, including our sun, including every star you can see in the night sky, and including brown dwarfs. The largest molecular clouds can contain up to 10 million solar masses of material, spread across a region hundreds of light years wide. The Orion Nebula is part of one of these giant molecular clouds. Inside that cloud, right now, new stars are being born. And some of them won't make it. Some of them will become brown dwarfs. The temperature inside these clouds is extraordinarily cold, about 10 to 20 Kelvin, roughly minus 250 to minus 260 degrees Celsius. The cold is actually important because it keeps the gas from moving too fast. If the gas were too hot, the particles would move too quickly for gravity to pull them together. The cold allows gravity to win. Here's how it begins. Within a molecular cloud, the gas is not perfectly evenly distributed. There are regions that are slightly denser than others. Maybe a shock wave from a nearby supernova explosion passes through the cloud, compressing the gas. Maybe two clouds collide. Maybe the gravitational influence of a passing star creates a disturbance. Whatever the cause, some region of the cloud ends up with a little more mass concentrated in a smaller space. And now, gravity takes over. That slightly denser region has slightly stronger gravity than its surroundings, so it starts pulling in more gas from nearby. As more gas falls in, the gravitational pull gets even stronger, which pulls in even more gas, which makes the pull even stronger still. This is a runaway process. Once it starts, it feeds on itself. Astronomers call this gravitational collapse, and it's the first step in the birth of every star. The collapse doesn't happen overnight. It takes hundreds of thousands of years, or even a few million years. But by cosmic standards, that's fast. The Milky Way is over 13 billion years old. Star formation happens in the blink of a cosmic eye. As the gas collapses inward, the cloud also begins to rotate. Just as an ice skater spins faster when they pull their arms in, the collapsing gas spins faster as it contracts. This rotation flattens the cloud into a disk shape with the densest concentration of material at the center. This central concentration is where the future star or brown dwarf will form. The surrounding disk is where planets may eventually take shape. It's a common origin story shared by stars and brown dwarfs alike. As the gas collapses inward, something important happens. It heats up. This isn't mysterious or surprising if you think about it. When you pump air into a bicycle tire, the pump gets warm. That's because compressing a gas increases its temperature. The same thing happens on a cosmic scale. As gravity compresses the collapsing cloud of hydrogen, the gas at the center gets hotter and hotter. The particles move faster. They collide more often. The pressure increases. At first, the collapsing cloud is cool. The gas might be only about 10 degrees above absolute zero. But as the collapse continues, as more and more gas piles up at the center, the temperature rises steadily. Within a few 100,000 years, the center of the collapsing cloud has reached thousands of degrees, then tens of thousands, then hundreds of thousands. The object that's forming at the center of this collapse is called a protostar. It's not a star yet. It's glowing, yes, because anything that's hot emits light. But it's not generating energy the way a real star does. The protostar is hot because of gravitational compression. It's turning gravitational potential energy into thermal energy. Think of it like heating something by squeezing it. The energy has to go somewhere, and it goes into heat. Now here's the crucial part. As the protostar continues to contract and heat up, it reaches a point where something entirely new begins to happen. Something that transforms it from just a hot ball of gas into something fundamentally different. It begins nuclear fusion. Nuclear fusion is the process that powers every star in the universe. It's what makes the sun shine. It's what produces the light and heat that makes life on Earth possible. And understanding fusion is essential to understanding why brown dwarfs are not stars. Here's what happens at the atomic level. A hydrogen atom consists of one proton and one electron. The proton sits at the center, the nucleus, and the electron orbits around it. In the core of a protostar, the temperatures are so extreme that atoms can't hold onto their electrons. The electrons are stripped away, and you're left with a soup of bare protons and free electrons. This state of matter is called plasma. Now, protons are positively charged, and like charges repel each other. If you try to push two protons together, they resist. There's an electromagnetic force pushing them apart. Under normal conditions, this force wins. Protons simply cannot get close enough to each other. This is called the Coulomb barrier, and it's the reason hydrogen gas doesn't just spontaneously fuse into helium at room temperature. If it did, every balloon filled with hydrogen would be a nuclear bomb. But in the core of a collapsing protostar, conditions are anything but normal. The temperatures are so high that the protons are moving incredibly fast. They're slamming into each other at tremendous speeds, and the pressure is so extreme that they're packed incredibly close together. Under these conditions, something remarkable happens. The protons get close enough that another force takes over. The strong nuclear force. The strong nuclear force is one of the four fundamental forces of nature, along with gravity, electromagnetism, and the weak nuclear force. It's called the strong force because it's the strongest of the four, about 100 times stronger than electromagnetism. But it only works at incredibly short distances, roughly the width of a proton. At distances larger than this, the strong force is essentially zero. It doesn't reach. It has no effect. So here's the situation. Two protons are being pushed apart by the electromagnetic force, which works at any distance. But if they can somehow get close enough, within about 1 femtometer, which is a millionth of a billionth of a meter, the strong nuclear force kicks in and overpowers the electromagnetic repulsion. The protons snap together. They fuse. And when they fuse, they release energy. A tremendous amount of energy. The specific process that powers most stars, including our sun, is called the proton-proton chain. It's a series of reactions that ultimately takes 4 hydrogen nuclei, 4 protons, and fuses them into one helium nucleus, which contains 2 protons and 2 neutrons. Along the way, 2 of the protons are converted into neutrons through a process involving the weak nuclear force. Positrons and neutrinos are released in these steps, and at the end of the chain, the helium nucleus that comes out has slightly less mass than the 4 hydrogen nuclei that went in. Where did that mass go? It was converted into energy. This is Einstein's famous equation, E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is an enormous number, about 300,000 kilometers per second. When you square it, you get an even more enormous number. So even a tiny amount of mass converts into a staggering amount of energy. In the proton-proton chain, about 0.7% of the original mass is converted to energy. That might sound small, but consider the numbers involved. The sun converts about 600 million tons of hydrogen into helium every single second. Of that 600 million tons, about 4.3 million tons are converted directly into energy every second. The sun has been doing this for about 4.6 billion years, and it has enough hydrogen fuel to continue for roughly another 5 billion years. But here's the thing that makes fusion in a star special. It's not just that fusion happens, it's that fusion sustains itself. It's self-regulating. And this self-regulation is what separates a true star from everything else. When fusion ignites in the core of a protostar, it releases enormous amounts of energy. That energy creates an outward pressure, radiation pressure, and thermal pressure combined that pushes against the inward pull of gravity. If the fusion rate increases, more energy is produced. The core heats up, it expands slightly, and the expansion cools the core, which slows the fusion rate back down. If the fusion rate decreases, less energy is produced. The core cools, gravity compresses it a bit more, the compression heats it up, and fusion increases again. This balance is called hydrostatic equilibrium. It's one of the most important concepts in stellar physics. A star in hydrostatic equilibrium is perfectly balanced. Gravity pulling inward equals pressure pushing outward. The star neither collapses nor explodes. It just sits there, steadily fusing hydrogen in its core, producing a constant stream of energy that radiates outward as light and heat. This equilibrium is what makes a star. Not just that fusion happens, but that it continues. Stably. For millions or billions of years. A star is a self-sustaining nuclear reactor held together by gravity and held apart by its own energy output. It's a machine that runs on its own fuel, producing exactly the right amount of energy to prevent its own collapse without blowing itself apart. Now, the critical question: what determines whether a collapsing cloud of gas achieves this? What determines whether fusion ignites and sustains itself? The answer is mass. Specifically, a minimum mass. Not every collapsing cloud of gas becomes a star. If the cloud doesn't have enough mass, gravity can't compress the core enough. The temperature never gets high enough. The pressure never gets extreme enough. The protons never move fast enough or get close enough for the strong nuclear force to take over. Fusion never ignites, or if some limited fusion reactions occur, they can't sustain themselves. The minimum mass required for sustained hydrogen fusion is approximately 0.08 solar masses. That's about 8% of the mass of our Sun. To put this in more familiar terms, it's roughly 75 to 80 times the mass of Jupiter. Jupiter is the largest planet in our solar system. It's massive by planetary standards, containing more mass than all the other planets combined. Its diameter is about 11 times Earth's. Its volume could hold more than 1,300 Earths. And yet, to become even the smallest, dimmest, most marginal star possible, you need roughly 80 Jupiters worth of mass, all compressed together. This threshold isn't arbitrary. It's set by the laws of physics. The temperature required for sustained hydrogen fusion in the core is approximately 10 million Kelvin. At temperatures below this, protons simply don't have enough kinetic energy to overcome the Coulomb barrier, frequently enough for fusion to become self-sustaining. Individual fusion reactions might occur occasionally through a process called quantum tunneling, where a proton essentially passes through the energy barrier rather than going over it. But these rare events aren't enough to generate the energy needed to maintain hydrostatic equilibrium. The core can't produce enough outward pressure to balance gravity, and the object continues to contract. Quantum tunneling itself is worth understanding here because it plays a crucial role. Classical physics would tell you that the temperatures in stellar cores aren't actually high enough for fusion. If protons were just classical particles, they would need even higher temperatures to overcome the Coulomb barrier directly. But protons are quantum objects. They don't have a precise location. Instead, they have a probability distribution. There's a small but non-zero chance that a proton is on the other side of the energy barrier. even if it doesn't have enough energy to climb over it. This is quantum tunneling. It's a real physical phenomenon, confirmed by countless experiments. Without it, the sun couldn't shine, stars wouldn't exist, and neither would we. But quantum tunneling only works well enough to power a star, if the conditions are right. The protons need to be packed closely enough and moving fast enough for these tunneling events to happen frequently enough, and that requires a core temperature of roughly 10 million Kelvin and the corresponding enormous pressures that only come from having enough mass piled on top. Below 0.08 solar masses, you don't get there. The core gets hot, yes. It gets compressed, yes. But not enough. The temperature might reach a few million Kelvin. It might even approach the threshold, but it never crosses it in a sustained way. The object glows for a while from the heat of gravitational contraction. It might even undergo some limited nuclear reactions, but it never achieves hydrostatic equilibrium through hydrogen fusion. It never becomes a self-sustaining nuclear furnace, and this is where the story of brown dwarfs begins. Above 0.08 solar masses, you get a star. The core ignites. Hydrogen fusion begins and sustains itself. The object achieves hydrostatic equilibrium. It shines steadily for millions, billions, or even trillions of years depending on its mass. The smallest stars, those just barely above the threshold, are called red dwarfs. They're dim, cool, and incredibly long-lived. A red dwarf with a mass of about 0.08 solar masses has a surface temperature of only about 2000 degrees Celsius. It glows a deep red, barely visible to the human eye. It produces only about 1/10,000th the luminosity of the sun, but it's a star. It's fusing hydrogen in its core. It's in hydrostatic equilibrium. It will continue shining for trillions of years, far longer than the current age of the universe. These red dwarfs are actually the most common type of star in the galaxy. About 70% of all stars in the Milky Way are red dwarfs. They're so dim that none of them are visible to the naked eye from Earth, even though many are relatively close. Proxima Centauri, the nearest star to our Sun, is a red dwarf. It's only about 4.24 light years away, but you need a telescope to see it because it's so faint. When you look up at the night sky, every single star you see is brighter and more massive than a red dwarf. The stars visible to your eyes represent the top fraction of the stellar population. The most common stars in the universe are invisible to you without technology. Red dwarfs are so efficient with their fuel, burning hydrogen so slowly that they will outlive almost everything else in the cosmos. Long after our sun has exhausted its fuel, swelled into a red giant, and collapsed into a white dwarf, the smallest red dwarfs will still be quietly shining. Now, consider how narrow the margin is. A red dwarf star at 0.08 solar masses is fusing hydrogen. It's a star. But an object at 0.075 solar masses, just slightly less massive, cannot sustain hydrogen fusion. It's not a star, it's a brown dwarf. The difference between a star and a brown dwarf can come down to a few Jupiter masses worth of material. That's an incredibly thin line considering the scales involved. A few Jupiter masses might sound like a lot, and it is by human standards. Jupiter is more massive than all the other planets in our solar system combined. But in the context of stellar formation, where molecular clouds contain thousands or millions of solar masses worth of material, a few Jupiter masses is almost nothing. It's a rounding error, a cosmic coin flip. This is what makes brown dwarfs so fascinating. They formed the same way stars did. They went through the same process. A region of a molecular cloud collapsed under gravity, gas compressed, temperatures rose, a protostellar object formed at the center. Everything was proceeding along the path to becoming a star, but there wasn't quite enough mass. Maybe the surrounding cloud was dispersed by radiation from a nearby massive star before enough material could accumulate. Maybe the cloud fragment that collapsed was simply smaller than average. Maybe a gravitational interaction with a neighboring protostar stripped away material before the core could gather enough. Whatever the reason, the result was the same. The core got hot, but not hot enough. The pressure was enormous, but not enormous enough. The protons were moving fast, but not fast enough. Imagine running toward a cliff edge with the intention of jumping across to the other side. You sprint as hard as you can. You leap, and you almost make it. Your fingers brush the far edge, but you fall short. Not because you did anything wrong, not because you failed, but because you simply didn't have enough momentum. You didn't have enough of what you needed. That's what happened to every brown dwarf in the universe. It ran as hard as physics would let it, but it didn't have enough mass to make the jump. And once the collapse stalls, once the core reaches its maximum temperature without igniting sustained fusion, there's no second chance. The object will never gain more mass. The window has closed. The mass threshold of 0.08 solar masses isn't something astronomers chose arbitrarily. It emerges directly from the physics. It comes from the interplay between gravity, the Coulomb barrier, quantum tunneling probabilities, and the thermodynamics of gas under extreme compression. In our universe, with our particular set of physical constants, the line falls at about 0.08 solar masses, and everything below that line, no matter how hot it gets, no matter how compressed, cannot sustain hydrogen fusion. This matters because it tells us something profound about how the universe organizes itself. Stars aren't just any hot ball of gas. They're objects that crossed a specific physical threshold. They achieved conditions in their cores that allow a self-sustaining nuclear reaction to proceed for cosmically significant timescales. Brown dwarfs are objects that came achingly close to that threshold, but never crossed it. They're not broken stars. They're not incomplete stars. They're objects that physics wouldn't let become stars because they lacked the one thing that matters most in this context: mass. To truly appreciate the difference, think about what it means for an object to sustain fusion versus merely experiencing some fusion. Our sun fuses about 600 million tons of hydrogen every second. It has done this for 4.6 billion years and will continue for 5 billion more. The fusion in its core is constant, stable, and self-regulating. It's like a perfectly tuned engine running smoothly for billions of years. A brown dwarf, by contrast, might experience some nuclear reactions in its core. As we'll explore shortly, many brown dwarfs can fuse deuterium, a heavier form of hydrogen. But this is not the same thing as what the sun does. Deuterium fusion is brief, limited, and doesn't produce nearly enough energy to establish hydrostatic equilibrium. It's like striking a match versus lighting a furnace. The match produces heat and light, yes, but it burns out quickly. The furnace, once lit, can run indefinitely as long as fuel is supplied. Stars are furnaces, brown dwarfs are matches. Understanding this distinction, understanding the physics of what makes a star, is essential before we can truly grasp what a brown dwarf is. Because a brown dwarf is not defined by what it is. It's defined by what it almost was. It's defined by a threshold it never crossed. And that threshold, the minimum mass for sustained hydrogen fusion, is one of the most important boundaries in astrophysics. There's something almost poetic about this boundary. It's sharp in theory, but messy in practice. The transition from the lowest mass stars to the highest mass brown dwarfs happens over a very narrow range. Objects just above the line are barely functioning stars, glowing dimly, fusing hydrogen sluggishly, producing just enough energy to hold themselves up against gravity. Objects just below the line are almost stars, their cores nearly hot enough, nearly dense enough, tantalizingly close to ignition, but never quite reaching it. And both kinds of objects look remarkably similar from the outside. A low-mass red dwarf and a high-mass brown dwarf can have similar surface temperatures, similar sizes, and similar luminosities, at least for a while. The difference is internal. It's about what's happening in the core. One has crossed the threshold into sustained fusion. The other has not. One will shine for trillions of years. The other will slowly cool and fade into darkness. This is the foundation we need. A star shines because gravity compresses its core to conditions extreme enough for sustained hydrogen fusion. This fusion creates an outward pressure that balances gravity, establishing hydrostatic equilibrium, a stable self-regulating state that can last for cosmically vast timescales. The minimum mass for this is approximately 0.08 solar masses, roughly 80 times the mass of Jupiter. Below this threshold, the core never gets hot enough, never gets dense enough, and the object never achieves self-sustaining fusion. And below that threshold is where brown dwarfs live, in a space between planets and stars, too massive to be merely planetary, too light to ignite, caught in a gap that the laws of physics carved into the universe billions of years ago. Every brown dwarf that exists is a testament to that gap, a physical record of where the universe draws the line between a star and everything else, how it takes to become a star. You need enough mass for gravity to compress your core to roughly 10 million Kelvin. You need sustained hydrogen fusion, you need hydrostatic equilibrium, and you need at least about 0.08 solar masses, roughly 80 times the mass of Jupiter, to get there. Below that threshold, the universe says no. You don't get to be a star. But that raises an obvious question. What happens to the objects that don't make it? What happens to the collapsing clouds of gas that gather 50 Jupiter masses, or 40 or 20? They went through the same formation process. They collapsed from the same molecular clouds. They heated up the same way. They just didn't gather enough material. Do they simply vanish? Do they dissipate back into space? No, they don't. They become something. They persist as real physical objects drifting through the galaxy, radiating heat, sometimes orbiting other stars, sometimes wandering alone through interstellar space. They become brown dwarfs, and understanding what a brown dwarf actually is, what it does, what happens inside it, and why it behaves the way it does, that's where this story gets truly interesting. Because a brown dwarf isn't empty or inert. It's not just a lump of gas sitting passively in space. There's real physics happening inside, including nuclear reactions that most people don't know about. A brown dwarf has a story, and that story begins the same way every star's story begins. A brown dwarf is a substellar object. That word, substellar, tells you everything about how astronomers think about them. They're below the stellar threshold. They're objects that form the way stars form, but ended up below the mass needed for sustained hydrogen fusion. They occupy a mass range roughly between 13 Jupiter masses at the low end and about 80 Jupiter masses at the high end. Below 13 Jupiter masses, you're in the realm of giant planets. Above 80 Jupiter masses, you've crossed into red dwarf territory, the lowest mass true stars. Brown dwarfs live in the gap between these two boundaries. Now, let's talk about what happens inside a brown dwarf, because the interior physics is where everything becomes clear. Remember what we discussed about gravitational collapse? A cloud of gas collapses under gravity, the center compresses, the temperature rises. For a star, this process continues until the core reaches about 10 million Kelvin and hydrogen fusion ignites. But for a brown dwarf, the collapse proceeds the same way, at least initially. Gravity pulls the gas inward, the core compresses, the temperature climbs, a protostellar object forms at the center, glowing from the heat of gravitational contraction. From the outside, a young brown dwarf looks almost identical to a young low-mass star. Both are hot, both are luminous, both are embedded in disks of gas and dust. If you observe them from a distance during this early stage, you might not be able to tell the difference, but something different happens inside. As the brown dwarf's core compresses and heats up, it reaches temperatures of a few million Kelvin. That's hot. Incredibly hot by any earthly standard. Hot enough to melt any known material. Hot enough that the gas is fully ionized into plasma. But it's not hot enough. Not for hydrogen fusion. The core needs 10 million Kelvin for sustained hydrogen fusion, and a brown dwarf's core tops out at somewhere between roughly 1 million and 6 million Kelvin, depending on its mass. The most massive brown dwarfs, those close to the 80 Jupiter mass boundary, can get their cores up to 5 or 6 million Kelvin. That's tantalizingly close. But close isn't enough. The Coulomb barrier between ordinary hydrogen protons requires about 10 million Kelvin for fusion to become self-sustaining. At 5 or 6 million Kelvin, ordinary hydrogen fusion sputters. Some individual fusion reactions might occur through quantum tunneling, but the rate is far too low to generate enough energy to establish hydrostatic equilibrium. The core simply cannot produce enough outward pressure to balance gravity through hydrogen fusion alone. But here's what most people don't know. Brown dwarfs are not completely fusion-free. Many of them do fuse something. They just don't fuse ordinary hydrogen, they fuse deuterium. Deuterium is a special form of hydrogen, an isotope. Ordinary hydrogen, the most common form, has a nucleus consisting of just one proton. That's it. One proton, one electron. The simplest atom in the universe. But deuterium, sometimes called heavy hydrogen, has a nucleus containing one proton and one neutron. That extra neutron changes everything about how the nucleus behaves in fusion reactions. Here's why deuterium matters for brown dwarfs. Fusing deuterium is much easier than fusing ordinary hydrogen. The temperature required for deuterium fusion is only about 1 million Kelvin. Compare that to the roughly 10 million Kelvin needed for sustained hydrogen fusion. Deuterium fusion ignites at about 1/10 the temperature. This means that many brown dwarfs, even those with significantly less mass than the stellar threshold, can achieve deuterium fusion in their cores. Any brown dwarf above roughly 13 Jupiter masses has enough mass for gravity to compress its core to the temperatures needed for deuterium fusion. The core hits 1 million Kelvin. Deuterium nuclei begin colliding with ordinary hydrogen protons at sufficient speeds and pressures for the strong nuclear force to bind them together. The deuterium nucleus, containing one proton and one neutron, fuses with a proton to create helium-3, a light isotope of helium with two protons and 1 neutron. This reaction releases energy in the form of a gamma-ray photon. This is real nuclear fusion. It's a genuine nuclear reaction releasing genuine nuclear energy. And when it's happening, the brown dwarf brightens. It produces energy from its core just like a star does. So, why isn't this enough? Why doesn't deuterium fusion make a brown dwarf a true star? The answer comes down to fuel supply. Deuterium is rare, extremely rare. In the universe, for roughly every 100,000 ordinary hydrogen atoms, there are only about 1 to 2 deuterium atoms. That's a ratio of roughly 1 in 65,000 to 1 in 50,000. Even though a brown dwarf contains an enormous amount of hydrogen, the fraction that's deuterium is vanishingly small. It's like having an enormous fuel tank that's 99.998% filled with a fuel you can't burn, and only 0.002% filled with a fuel you can. Most of this deuterium was created in the first few minutes after the Big Bang during a period called Big Bang nucleosynthesis. In those first minutes, the universe was still hot and dense enough for nuclear reactions to occur everywhere. Protons and neutrons collided and fused, creating deuterium, helium, and trace amounts of lithium. Most of the deuterium produced was quickly consumed in further reactions that built helium. The small amount that survived, roughly 26 parts per million by number relative to hydrogen, is essentially all the deuterium the universe will ever have. Stars destroy deuterium when they process it in their cores, so the cosmic abundance has been slowly declining over the age of the universe. This means that a brown dwarf supply of deuterium fuel is incredibly limited from the very beginning. When deuterium fusion ignites in a brown dwarf's core, it burns through the available deuterium relatively quickly. For the most massive brown dwarfs, this deuterium burning phase might last a few 100 million years. For lower mass brown dwarfs, it might last only a few tens of millions of years. Either way, by cosmic standards, it's brief. Compare that to the sun's hydrogen-burning lifetime of about 10 billion years, or a low-mass red dwarf's lifetime of trillions of years. Deuterium burning is a flash in the pan, a brief flare of nuclear energy that quickly exhausts itself. And here's the critical difference. When the deuterium runs out, that's it. There's no next step for a brown dwarf. A true star, when it exhausts the hydrogen in its core, can often transition to burning helium or heavier elements, depending on its mass. Stars have layers of fuel they can work through over their lifetimes, but a brown dwarf can't even sustain the first rung on that ladder. It can't fuse ordinary hydrogen. So when the tiny supply of deuterium is consumed, the brown dwarf has no energy source left. Fusion stops entirely. The core goes quiet. Think of it this way. Imagine you're trying to start a campfire. You have a small handful of kindling, thin, dry twigs that catch fire easily. That's the deuterium. It burns quickly and produces some heat and light. But to keep a fire going, you need larger logs. Those logs are ordinary hydrogen, and the brown dwarf never gets hot enough to ignite the logs. The kindling flares up, burns bright for a moment, and then goes out. And you're left sitting in the dark with a pile of logs you can never light. After the deuterium is exhausted, the brown dwarf enters a long, quiet decline. It still has enormous amounts of ordinary hydrogen in its core, vast reserves of potential fuel, but that fuel is permanently inaccessible. The temperatures will never be high enough. The conditions will never be right. It's like sitting on top of an oil reserve with no drill. The energy is there, locked inside the hydrogen atoms, but the brown dwarf has no way to extract it. This is perhaps the most poignant aspect of a brown dwarf's existence. It's not that it lacks fuel, it's surrounded by fuel, it's made almost entirely of fuel, but it can never use it. It's worth pointing out that deuterium fusion also doesn't establish true hydrostatic equilibrium the way hydrogen fusion does in a star. The energy produced by deuterium burning is simply not enough, relative to the brown dwarf's mass and gravitational compression, to create the kind of stable, self-regulating balance that defines a star. Deuterium burning in a brown dwarf is modest compared to the gravitational forces at play. The brown dwarf continues to slowly contract even while deuterium is burning. The burning slows the contraction somewhat, but it doesn't stop it. There's no stable equilibrium achieved. So deuterium fusion is real, but it's not enough. It doesn't make a brown dwarf a star. It doesn't establish hydrostatic equilibrium. And it doesn't last. Once the deuterium is gone, the brown dwarf is left with no internal energy source at all. From that point forward, it simply cools, slowly, steadily, inevitably, like a coal pulled from a fire. It glows for a while from residual heat, but it's not generating new heat. It's just losing what it has. Now we need to talk about something else that happens inside a brown dwarf. Something equally important to understanding why it never becomes a star. And this involves a concept from quantum mechanics that might sound exotic but is absolutely essential. Electron degeneracy pressure. Remember, as gravity compresses a brown dwarf's core, the density increases. The matter gets packed tighter and tighter. In a normal gas, if you compress it, the particles move faster and the temperature rises. Compress it more, the temperature rises more. This is what happens in the core of a collapsing protostar, on its way to becoming a star. Gravity compresses, temperature rises, and eventually the temperature gets high enough for fusion. But there's a limit to how much you can compress matter, and that limit comes from quantum mechanics. Specifically, it comes from something called the Pauli exclusion principle. The Pauli exclusion principle states that no two fermions can occupy the same quantum state simultaneously. Electrons are fermions. This means that no two electrons in the same region of space can have exactly the same energy, momentum, and spin. They're forced to be different from each other. What does this mean for a brown dwarf? As gravity compresses the core, the electrons get packed closer and closer together. At some point, they start running out of available quantum states. The low energy states get filled first. As more electrons are packed in, they're forced into higher and higher energy states, simply because all the lower states are already occupied. These high-energy electrons exert a pressure, a quantum mechanical pressure that resists further compression. This is electron degeneracy pressure. It has nothing to do with temperature. It has nothing to do with thermal energy. It's a purely quantum mechanical effect arising from the fundamental nature of electrons as fermions. In a normal star, the core is supported against gravity primarily by thermal pressure, the pressure generated by hot particles moving around and colliding. This thermal pressure is directly related to temperature, which is directly related to the rate of nuclear fusion. That's why stars are self-regulating. Change the fusion rate, you change the temperature, which changes the pressure, which brings the star back to the equilibrium. But in a brown dwarf, something different happens. As the core compresses and the density increases, electron degeneracy pressure kicks in before the temperature gets high enough for sustained hydrogen fusion. The degenerate electrons resist further compression. They push back against gravity. And this resistance halts the collapse, not because the core is hot enough to fuse hydrogen, not because nuclear energy is providing outward pressure, but because quantum mechanics simply won't allow the electrons to be compressed any further without occupying forbidden quantum states. This is the key mechanism. This is why brown dwarfs never become stars. It's not just that they don't have enough mass, it's that a specific physical process, electron degeneracy pressure, intervenes at precisely the wrong moment. It kicks in too early. Before the temperature can reach the critical threshold, if somehow you could turn off electron degeneracy pressure, if electrons didn't obey the Pauli exclusion principle, then a brown dwarf's core would continue compressing. The temperature would continue rising, and eventually even a 50 Jupiter mass object might reach 10 million Kelvin and ignite hydrogen fusion. But you can't turn off quantum mechanics. The Pauli exclusion principle is a fundamental law of nature, as inviolable as gravity itself. And so the compression halts, the temperature plateaus, and the brown dwarf is left forever short of the finish line. In a true star, gravity compresses the core until thermal conditions allow hydrogen fusion, and then fusion provides the energy to support the star against further collapse. The sequence is gravity compresses, temperature rises, fusion ignites, pressure balances gravity. Each step leads to the next. In a brown dwarf, gravity compresses the core, the temperature rises, but before the temperature reaches the hydrogen fusion threshold, electron degeneracy pressure steps in and halts the compression. The sequence is interrupted. Gravity compresses, temperature rises, degeneracy pressure stops compression, and the temperature plateaus below the fusion threshold. The core stabilizes not because fusion is providing energy, but because quantum mechanics has erected a wall that gravity cannot push past. This is a fundamentally different kind of support. In a star, the support is dynamic. It depends on ongoing fusion. If you could somehow stop fusion in the sun, the thermal pressure would decrease and the sun would collapse. The support is active. In a brown dwarf, the support is static. It doesn't depend on any energy source. Electron degeneracy pressure doesn't require fuel. It doesn't run out. It's a consequence of the fundamental quantum properties of electrons. A brown dwarf supported by electron degeneracy pressure will remain supported essentially forever. It won't collapse further, but it also won't ignite. It's stuck. This is why the term failed star is both misleading and revealing at the same time. It's misleading because it suggests that the brown dwarf tried to become a star and couldn't, as if it attempted fusion and the attempt failed. That's not what happens. Electron degeneracy pressure prevents the core from ever reaching the conditions needed for sustained hydrogen fusion. The brown dwarf didn't try and fail, it was prevented from trying. The door was closed before it could walk through. But the term is revealing in another sense. It tells you that brown dwarfs are closer to stars than they are to planets in terms of how they formed. They emerged from the same process. They're the same type of object. They just didn't have enough mass to cross the threshold. They're not failed in the sense of broken or defective. They're below the line that physics draws between objects that sustain hydrogen fusion and objects that don't. Let me make the electron degeneracy pressure concept even more concrete because it's so central to this story. Think of a parking garage with a fixed number of spaces on each level. Cars start filling the garage from the ground floor up. Each space can hold exactly one car. As more cars arrive, lower levels fill up and cars are directed to higher and higher floors. Eventually, even the top floor fills up. Now, if more cars try to enter, they can't. There's no room. Every available space is occupied. The garage resists accepting more cars, not because of any active mechanism, but because of the fundamental rule that only one car fits in each space. Electrons in a highly compressed brown dwarf core work the same way. Each quantum state is like a parking space. Only one electron can occupy each state at a time. As the core compresses and electrons are forced closer together, the available low-energy states fill up. Electrons are pushed into higher energy states. These high-energy electrons move faster and exert more pressure. Eventually, the pressure from these degenerate electrons is strong enough to halt the gravitational compression entirely. Here's something fascinating about this. Because electron degeneracy pressure doesn't depend on temperature, it creates a counterintuitive situation. In normal materials, if you heat something, it expands. If you cool it, it contracts. But in a degenerate gas, temperature and pressure are disconnected. You can cool the gas without it contracting because the degeneracy pressure doesn't change. The brown dwarf's core can cool over billions of years, radiating away its thermal energy, and it will stay the same size. The electrons don't care about the temperature. They're still in their quantum states, still exerting the same pressure, still holding the core up against gravity. This is why brown dwarfs are roughly the same size regardless of their mass. This might sound strange, but it's true, and it's one of the most remarkable consequences of degeneracy physics. A brown dwarf with 13 Jupiter masses and a brown dwarf with 70 Jupiter masses are roughly the same physical size, both approximately the diameter of Jupiter, roughly about 140,000 kilometers across. That means you could have an object with 5 times the mass of another, and they would be nearly identical in diameter. The extra mass just gets compressed into the same volume. In fact, the more massive brown dwarfs can actually be slightly smaller than the less massive ones, because the stronger gravity in a more massive brown dwarf compresses the degenerate gas more tightly. More mass, same size or even smaller. It's completely backwards from our everyday intuition, where bigger things tend to be heavier and heavier things tend to be bigger. Compare this to stars, where size varies enormously with mass because their support comes from thermal pressure, which scales with the fusion rate, which scales with mass. Brown dwarfs, supported by degeneracy pressure, all end up roughly Jupiter-sized. All that extra mass is packed into essentially the same volume, making brown dwarfs incredibly dense compared to gas giant planets like Jupiter. This density tells you something about the conditions inside. A typical brown dwarf might have a density in its core of tens to hundreds of grams per cubic centimeter. For comparison, water has a density of 1 gram per cubic centimeter. Iron has a density of about 7.87 grams per cubic centimeter. Gold has a density of about 19.3 grams per cubic centimeter. The core of a brown dwarf is denser than gold, denser in some cases than platinum. Material packed so tightly that the electrons have been squeezed into a degenerate state where quantum mechanics takes over from ordinary gas physics. The conditions inside a brown dwarf's core are closer to the conditions inside a white dwarf, the dense remnant left behind when a sun-like star dies, than they are to the conditions inside Jupiter. Even though a brown dwarf looks like an oversized Jupiter from the outside, the interior physics is radically different. Jupiter's core is compressed and hot, yes, but it hasn't reached the point where electron degeneracy dominates. a brown dwarf has. The inside of a brown dwarf is a quantum mechanical object masquerading as a planet. Yet from the outside, it looks roughly like a large planet, same size as Jupiter, glowing dimly with residual heat, unremarkable to a casual observer. The extraordinary physics is hidden inside. So let's bring all of this together. A brown dwarf forms the same way a star does. A cloud of gas collapses under gravity. The center compresses and heats up. But the brown dwarf doesn't accumulate enough mass. Its core reaches temperatures of a few million Kelvin, enough for deuterium fusion but not enough for sustained hydrogen fusion. Deuterium fusion occurs, burning through the limited supply of deuterium in perhaps a few tens of millions to a few 100 million years. But this is temporary and insufficient to establish the kind of self-sustaining equilibrium that defines a true star. Meanwhile, as the core compresses, electron degeneracy pressure builds up and eventually halts further compression before the core can reach the 10 million Kelvin threshold needed for hydrogen fusion. The core stabilizes at a temperature below the fusion threshold, supported not by nuclear energy but by quantum mechanical pressure. And there the brown dwarf sits. Too massive to be a planet in the traditional sense, too light to be a star, glowing with residual heat from its formation and from its brief period of deuterium burning, slowly cooling, slowly fading. It's not a failed star in the sense that something went wrong. Everything that happened inside the brown dwarf proceeded exactly as physics dictates. Gravity compressed, temperature rose, degeneracy pressure halted further compression. These are not errors, they're consequences. The brown dwarf followed the rules perfectly. The rules just didn't lead to sustained hydrogen fusion because there wasn't enough mass for them to do so. Every brown dwarf in the universe is a physical record of this threshold. Every single one formed through gravitational collapse, heated up in its core, and stopped short of becoming a star because quantum mechanics intervened before the temperature could reach the critical level for sustained fusion. They sit in a narrow band of mass, roughly 13 to 80 times the mass of Jupiter, occupying a region of parameter space that the universe carved out between planets and stars. They're not anomalies. They're not mistakes. They're a natural and inevitable consequence of the way gravity, thermodynamics, nuclear physics, and quantum mechanics interact. The brown dwarf represents one of nature's most elegant dead ends. A path that starts the same way as the path to stardom, runs parallel to it for millions of years, but diverges at the last moment because of a difference of a few Jupiter masses worth of material, gathered from a primordial cloud of gas billions of years ago. The physics that creates stars also creates brown dwarfs. They're siblings separated at birth by a threshold that neither chose and neither can change. The star burns bright. The brown dwarf glows dim and slowly fades. Both are doing exactly what the laws of physics require them to do. So now we know what a brown dwarf is. An object that formed through gravitational collapse, just like a star, but didn't accumulate enough mass to sustain hydrogen fusion in its core. It might fuse deuterium for a while, but that's temporary and insufficient. Electron degeneracy pressure halts further compression before the core reaches the temperatures needed for sustained fusion. The brown dwarf glows with residual heat and slowly cools over billions of years. It's not a star, but it's not a planet either. And this is where things get genuinely complicated. Because the universe doesn't draw clean lines. We draw lines. Humans love categories. We love putting things in boxes. Star, planet, moon, asteroid. We want every object in the universe to fit neatly into one of our categories. But the universe doesn't care about our categories. It produces a continuous spectrum of objects, from the smallest dust grains to the most massive stars, and the boundaries between our categories are often blurry, debated, and sometimes almost arbitrary. Brown dwarfs sit right in the middle of one of the blurriest boundaries in all of astrophysics. They're caught between two categories, too massive for one, too light for the other, and the borders on both sides are messy. Let's start with the upper boundary, the line between a brown dwarf and a true star. We've discussed this threshold already. It's approximately 0.08 solar masses, roughly 75 to 80 Jupiter masses. Above this line, you get sustained hydrogen fusion. Below it, you don't. This sounds clean and precise, but in practice, the boundary is surprisingly difficult to pin down for a specific object. The problem is that the transition from brown dwarf to red dwarf star isn't a sudden switch. It's gradual. An object at exactly the threshold mass doesn't suddenly burst into stable fusion the way a light bulb turns on when you flip a switch. Instead, there's a narrow range of masses where fusion behavior is ambiguous. An object at, say, 78 Jupiter masses might fuse hydrogen at an extremely low rate, so low that it barely qualifies as sustained fusion. The energy output might be minimal. The core temperature might hover right around the threshold, sometimes just above, sometimes just below, as the object slowly contracts and adjusts over millions of years. Is this object a star or a brown dwarf? It depends on how strictly you define sustained fusion. At 75 Jupiter masses, an object might undergo brief episodes of hydrogen fusion that flicker on and off over millions of years before eventually ceasing entirely. The core gets just barely hot enough for some hydrogen fusion through quantum tunneling, but the rate is so low that it can't maintain true hydrostatic equilibrium. The object continues to slowly contract. As it contracts, the core heats up slightly, fusion increases briefly, then electron degeneracy pressure stiffens the core, the contraction slows, and fusion drops again. It's an object caught in a twilight zone between stellar and substellar, neither fully a star nor cleanly a brown dwarf. At 83 or 84 Jupiter masses, on the other hand, fusion is clearly sustained. The core is hot enough and the fusion rate is high enough to maintain equilibrium. The object is unambiguously a star, even if it's the dimmest, coolest, smallest star imaginable. A dim red ember, barely visible even with a telescope. The transition zone between these extremes spans roughly 5 to 10 Jupiter masses. In that narrow range, the behavior of an object is difficult to classify definitively without extremely precise measurements of its mass, luminosity, and age. Two objects with nearly identical masses might end up on different sides of the line, depending on subtle differences in their composition, particularly their metallicity, which is the fraction of elements heavier than helium they contain. Higher metallicity affects the opacity of the gas in the core, which influences how efficiently heat can escape, which in turn affects the internal temperature profile. A higher metallicity object might need slightly more mass to achieve the same core temperature as a lower metallicity object. So the exact threshold isn't a single universal number. It depends on the composition of the individual object. It shifts by a few Jupiter masses depending on the chemical makeup of the gas from which the object formed. This makes the upper boundary of the brown dwarf category somewhat fuzzy. Not hopelessly fuzzy. We know it's in the range of about 75 to 80 Jupiter masses. But for any individual object near that boundary, classification can be uncertain. Astronomers sometimes need to observe an object for years, measuring its luminosity carefully and comparing it to theoretical models of how objects at different masses evolve over time, before they can determine whether it's a very low-mass star or a very high-mass brown dwarf. The distinction often comes down to whether the object's luminosity is holding steady, which would indicate sustained fusion, or whether it's slowly declining, which would indicate a brown dwarf that's cooling. Now, let's look at the other boundary, the lower one, the line between a brown dwarf and a giant planet. And this is where things get really messy. The conventional boundary is set at about 13 Jupiter masses. This number comes from deuterium fusion. As we discussed, objects above about 13 Jupiter masses have enough mass for gravity to compress their cores to the roughly 1 million Kelvin needed for deuterium fusion. Below 13 Jupiter masses, even deuterium can't fuse. So the International Astronomical Union, which is the organization that officially names and classifies celestial objects, adopted this threshold as the dividing line. Above 13 Jupiter masses and below the hydrogen fusion threshold, you have a brown dwarf. Below 13 Jupiter masses, you have a planet. This sounds reasonable. There's a physical basis for the number. It's tied to a real nuclear process. But here's the problem. Many astronomers don't like this definition, and they have good reasons. First, deuterium fusion isn't a dramatic event. As we discussed in detail, deuterium is rare and burns out quickly. An object at 14 Jupiter masses will fuse deuterium for a relatively brief period and then stop. An object at 12 Jupiter masses won't fuse deuterium at all. But in virtually every other way, these two objects are nearly identical. They have similar sizes, similar temperatures, similar compositions, similar atmospheric chemistry. If you observe them side by side with a telescope, you might not be able to tell which one had fused deuterium and which hadn't. The deuterium fusion, while physically real, leaves almost no lasting signature. It's a brief episode early in the object's life that makes very little difference to its long-term evolution. So, defining the entire identity of an object, calling one a brown dwarf and the other a planet, based on whether or not it briefly fused a trace isotope early in its life seems, to many astronomers, arbitrary. It's like classifying humans into two fundamentally different categories based on whether they had a fever in their first year of life. The fever happened, sure, but it doesn't define who they are. Second, and this is the deeper issue, the 13 Jupiter mass boundary says nothing about how the object formed. And to many astronomers, formation is what should really matter. Because brown dwarfs and planets form in fundamentally different ways. Brown dwarfs form the way stars form, through the direct gravitational collapse of a cloud of gas. A region of a molecular cloud becomes gravitationally unstable, collapses inward, and a self-gravitating object forms at the center. This is the same process that creates stars. The only difference is the amount of mass that accumulates. Brown dwarfs are the low mass end of the star formation process. They're the runts of the stellar litter, the smallest objects produced by cloud collapse. Planets form differently. Planets form in the disk of gas and dust that surrounds a young star or brown dwarf after it forms. Within this protoplanetary disk, solid particles collide and stick together, building up larger and larger bodies. Dust grains become pebbles. Pebbles become rocks. Rocks become planetesimals. Planetesimals become planetary embryos. and planetary embryos become planets. This process is called core accretion. It builds planets from the bottom up, starting with small solid particles and gradually assembling larger objects through collisions and gravitational attraction. For gas giant planets like Jupiter, the process goes a step further. Once a rocky or icy core reaches about 10 Earth masses, its gravity becomes strong enough to capture and hold enormous amounts of hydrogen and helium gas from the surrounding disk. The planet rapidly balloons in size as gas falls onto the growing core. This is how Jupiter formed. A solid core built up through accretion, and then that core captured a massive envelope of hydrogen and helium. The result is a planet with a composition similar to a star, mostly hydrogen and helium, but with a fundamentally different formation history. So here's the question that divides astronomers. If you find a 15 Jupiter mass object orbiting a star, is it a brown dwarf or a planet? The 13 Jupiter mass definition says it's a brown dwarf because it's above the deuterium fusion threshold. But what if it formed through core accretion in a protoplanetary disk, the same way Jupiter formed, just with more mass? In that case, it formed like a planet. It's the product of a planetary formation process. Calling it a brown dwarf because of its mass seems misleading when its origin is entirely planetary. Conversely, what if you find a 10 Jupiter mass object floating freely through space, not orbiting any star? The 13 Jupiter mass definition says it's a planet, but how can it be a planet if it doesn't orbit a star? And what if it formed through direct gravitational collapse of a gas cloud, the same way stars and brown dwarfs form? In that case, it formed like a brown dwarf. Its formation history is stellar, not planetary. Calling it a planet because of its mass seems equally misleading. These aren't hypothetical scenarios. Astronomers have found objects in both categories. There are objects above 13 Jupiter masses, orbiting stars at distances, and in configurations that strongly suggest they formed through core accretion in a disk. And there are free-floating objects below 13 Jupiter masses, drifting through space that appear to have formed through cloud collapse. The mass-based definition fails in both cases. This is why some astronomers argue that the definition should be based on formation rather than mass. Under a formation-based definition, a brown dwarf is any object that formed through gravitational collapse of a gas cloud, but didn't achieve sustained hydrogen fusion. A planet is any object that formed through core accretion in a disk around a star or brown dwarf. Under this definition, a 10 Jupiter mass object that formed through cloud collapse would be a brown dwarf. Not a planet, even though it's below the deuterium fusion threshold. And a 15 Jupiter mass object that formed through core accretion would be a planet, not a brown dwarf, even though it's above the threshold. The problem with the formation-based definition is practical. How do you determine how an object formed? You can't go back in time and watch it form. You have to infer its formation history from the evidence available today, and that evidence is often ambiguous. Composition and orbital properties can offer clues, but these are statistical tendencies, not certainties. Gravitational interactions can change orbits over time, moving objects from where they formed to completely different locations. So neither definition is perfect. The mass-based definition is clean and easy to apply, but doesn't capture the physical distinction between formation mechanisms. The formation-based definition is more physically meaningful, but is often impossible to apply in practice because we can't determine how a specific object formed. This is a genuine ongoing debate in astronomy. Papers are published regularly arguing for one definition or the other. Conferences feature heated discussions about where exactly the line should be drawn, and for now, there's no consensus. The field uses the 13 Jupiter mass boundary as a working convention, while acknowledging that it's imperfect and that individual objects near the boundary may be misclassified. For our purposes, what matters is understanding that the lower boundary of the brown dwarf category is genuinely uncertain. The universe produces a continuous range of objects from a few Jupiter masses up through brown dwarf territory and into the stellar regime. There's no sharp physical discontinuity at 13 Jupiter masses. Deuterium fusion provides a convenient marker, but it's not a hard boundary that separates fundamentally different types of objects, the way sustained hydrogen fusion separates brown dwarfs from stars. The transition from giant planet to brown dwarf is smoother and more ambiguous than the transition from brown dwarf to star. Now, let's talk about how astronomers actually find and identify brown dwarfs, because discovering them is extremely challenging. Brown dwarfs are dim. They don't produce their own sustained energy through fusion, so they're much fainter than even the dimmest stars. A young brown dwarf might glow with a surface temperature of 2000 to 3000 Kelvin, giving off a dull reddish light. But an old brown dwarf that has been cooling for billions of years might have a surface temperature of only a few hundred Kelvin, barely warmer than boiling water. At those temperatures, the object emits almost entirely in the infrared. It's invisible to the naked eye and extremely faint even with optical telescopes. This is why brown dwarfs weren't confirmed to exist until 1995, even though theorists had predicted their existence decades earlier. The physics was clear. There had to be a minimum mass for hydrogen fusion, and objects below that mass had to exist as dark substellar objects drifting unseen through the galaxy. But predicting something exists and actually finding it are two very different things. Detecting these objects required technology that didn't exist yet. You need infrared sensitive detectors. You need telescopes optimized for infrared wavelengths. You need surveys that cover large areas of the sky looking for very faint, very red objects. The breakthrough came with improved infrared detector technology in the 1990s. Infrared detectors had been around for decades, but they were relatively insensitive and noisy. By the mid-1990s, new generations of infrared detectors made it possible to detect the faint infrared glow of cool substellar objects. And that's when the discoveries started rolling in. One of the key tools astronomers use to identify brown dwarfs is spectroscopy. When you spread the light from an object into a spectrum, different wavelengths reveal the presence of different molecules and atoms in the object's atmosphere. Stars, even cool red dwarf stars, are too hot for most molecules to survive in their atmospheres. At temperatures above about 3,500 Kelvin, most molecules break apart into individual atoms. So stellar spectra are dominated by atomic absorption lines, the signatures of individual elements like hydrogen, calcium, sodium, and iron. But brown dwarfs are cooler. Cool enough for molecules to form and survive in their atmospheres. And the specific molecules that appear depend on the temperature. In the warmest brown dwarfs, with surface temperatures between about 2,200 and 1,300 Kelvin, you see metal hydrides and metal oxides in the spectrum. These objects are classified as L dwarfs. As you move to cooler brown dwarfs, with temperatures between about 1300 and 500 Kelvin, methane becomes the dominant feature in the spectrum. Methane absorbs strongly at specific infrared wavelengths, creating distinctive dips in the spectrum that are easy to identify. These cooler objects are classified as T-dwarfs. The presence of methane is a dead giveaway. No star is cool enough for methane to exist in its atmosphere. If you see methane in the spectrum, you know you're looking at a brown dwarf or a very cool substellar object. The coolest brown dwarfs, those that have been cooling for billions of years, have surface temperatures below about 500 Kelvin. These are classified as Y dwarfs. They're so cool that water vapor and ammonia dominate their spectra. Some Y dwarfs have surface temperatures comparable to a warm oven, only a few hundred degrees Celsius. A handful of known Y dwarfs have surface temperatures below the boiling point of water. You could potentially touch the surface of these objects without being burned, although their crushing gravity, strong magnetic fields, and the fact that they're gaseous objects without a solid surface would make that a poor idea. The spectral classification system for brown dwarfs, L, T, and Y, extends the traditional stellar classification system that runs from O through M for stars. Brown dwarfs extend this sequence beyond ML dwarfs, are cooler than M dwarfs. T dwarfs are cooler than L dwarfs. Y dwarfs are cooler still. Importantly, the classification is based on spectral features, not on mass or formation history, which means the L category actually includes some very low mass stars as well as high mass brown dwarfs. The spectral class tells you about the object's current surface temperature and atmospheric chemistry, not necessarily whether it's a star or a brown dwarf. Another important detection method is direct imaging. With modern adaptive optic systems and space telescopes, astronomers can sometimes directly photograph brown dwarfs, particularly when they orbit nearby stars. The brown dwarf appears as a faint point of light near the much brighter star. This is challenging because stars are so much brighter than brown dwarfs that the star's glare overwhelms the brown dwarf's faint glow. Special techniques are needed to block the star's light, allowing the much dimmer companion to be seen. Coronagraphs, instruments that block light from a central source, are often used for this purpose. Another molecular signature that helps identify brown dwarfs is lithium. Lithium is a fragile element that's destroyed by nuclear reactions at relatively low temperatures. In any object that sustains hydrogen fusion, even marginally, the lithium in its interior is quickly consumed. The convective mixing in low-mass stars brings lithium-bearing material from the surface down to the hot core where it's destroyed. So after a few 100 million years, most low-mass stars have depleted their lithium. Brown dwarfs, however, never get their cores hot enough to destroy lithium efficiently. At least the lower-mass brown dwarfs preserve their primordial lithium essentially forever. So if you detect lithium in the spectrum of a cool, dim object, it's a strong indicator that the object is a brown dwarf rather than a low-mass star. This is called the lithium test, and it was one of the early methods used to confirm brown dwarf candidates. There is a caveat though. The lithium test doesn't work for all brown dwarfs. The most massive brown dwarfs, those above roughly 65 Jupiter masses, have cores hot enough to destroy lithium over time, just as stars do. So the absence of lithium doesn't necessarily mean an object is a star. It might be a high-mass brown dwarf that burned through its lithium without ever achieving sustained hydrogen fusion. the test works best for lower mass brown dwarfs, where lithium survival is essentially guaranteed. Water vapor is another important spectral feature. Brown dwarfs are cool enough for water vapor to exist in their atmospheres. The absorption bands of water vapor are prominent in the infrared spectra of T and Y dwarfs. These bands are distinctive and help astronomers identify brown dwarfs in large infrared surveys. Wide-field infrared surveys have been the most productive method for finding brown dwarfs in large numbers. The 2-micron all-sky survey, known as 2MASS, conducted in the late 1990s, catalogued millions of infrared sources across the entire sky. By searching this catalogue for very red, very faint objects, with colours consistent with cool substellar atmospheres, astronomers identified hundreds of L and T dwarf candidates. Many of these were subsequently confirmed as brown dwarfs through follow-up spectroscopy. The Wide Field Infrared Survey Explorer, known as WISE, launched by NASA in 2009, pushed even further into the infrared. WISE surveyed the entire sky at wavelengths longer than those covered by 2MASS, making it sensitive to even cooler objects. WISE was responsible for discovering most of the known Y dwarfs, the coldest class of brown dwarfs. One of the most remarkable discoveries was WISE 0855-0714, a Y dwarf with a temperature estimated at about 250 Kelvin, roughly minus 23 degrees Celsius. That's below the freezing point of water. This object, located about 7.2 light years from Earth, making it one of the closest known substellar objects, is colder than many places on Earth's surface. It's a fascinating reminder that not everything in the cosmos is hot and fiery. Some objects in the universe are genuinely cold. They just happen to be several times more massive than Jupiter, or in the case of heavier brown dwarfs, dozens of times more massive. The James Webb Space Telescope, launched in 2021, has further revolutionized brown dwarf science. Its unprecedented infrared sensitivity allows it to detect and characterize brown dwarfs that are too faint for any previous telescope. Webb can study the atmospheres of brown dwarfs in extraordinary detail, identifying individual molecular species and mapping temperature variations across their surfaces. Some brown dwarfs have been found to have banded atmospheric patterns similar to Jupiter's cloud bands. Others show evidence of weather with clouds forming and dissipating over time, creating variability in the object's brightness. Brown dwarfs, it turns out, have weather. Not weather driven by energy from a parent star like the weather on Earth, but weather driven by the object's own internal heat, radiating outward through a complex dynamic atmosphere. These observations have revealed that brown dwarf atmospheres are surprisingly complex. They contain layers of clouds made of exotic materials. In the warmer L dwarfs, the clouds might be made of iron droplets and silicate grains, tiny particles of molten iron and rock condensing in the atmosphere like water droplets condense in Earth's clouds. As the brown dwarf cools into the T dwarf regime, these clouds sink below the visible photosphere, and the atmosphere clears. Methane becomes dominant. The object transitions from a cloudy reddish appearance to a clearer, more bluish methane-dominated appearance. This transition from L to T dwarf is not gradual. It happens relatively abruptly over a narrow temperature range, creating what astronomers call the LT transition. Understanding this transition is an active area of research, because it involves complex cloud physics, atmospheric dynamics, and radiative transfer in conditions that have no analog on Earth or anywhere else in the solar system. The detection and characterization of brown dwarfs has been one of the great success stories of modern astronomy. In the span of about 3 decades, we've gone from having no confirmed brown dwarfs to knowing of thousands. We've mapped out their spectral properties, their temperature ranges, their atmospheric chemistry, and their distribution throughout the galaxy. We've found them orbiting stars, orbiting each other in binary brown dwarf systems, and drifting alone through interstellar space. We found them in star-forming regions where they're young and bright, and in the galactic halo where they're old and dim. They're everywhere. The galaxy is full of them. And this brings us back to the fundamental question of classification. On the upper end, the boundary with stars is relatively clear, anchored in the well-understood physics of hydrogen fusion. On the lower end, the boundary with planets is genuinely fuzzy. The 13 Jupiter mass deuterium burning limit provides a convenient line, but it doesn't capture the physical distinction between objects that formed through cloud collapse and objects that formed through disk accretion. What makes this debate more than just academic categorization is that it touches on how nature works. Sustained hydrogen fusion is a real physical threshold that creates a genuine distinction between stars and brown dwarfs. Stars shine for billions of years. Brown dwarfs cool and fade. That's a real, observable, important difference. But the boundary between brown dwarfs and planets is much less clear, and we're left with the uncomfortable realization that the universe doesn't always organize itself into the neat categories we prefer. For now, what we can say with confidence is this: brown dwarfs are real objects that exist in enormous numbers throughout the galaxy. They share their formation mechanism with stars, but lack the mass for sustained hydrogen fusion. They sit in a physical gap that the universe carved between two much more familiar types of objects. A gap that turns out to be far more populated, far more interesting, and far more scientifically rich than anyone imagined before we developed the technology to peer into it. So we've established what brown dwarfs are, how they form, what happens inside them, and how they sit in a contested space between planets and stars. But there's a question we haven't fully addressed yet. What happens to them over time? Because a brown dwarf's life, if you can call it that, is unlike anything else in the cosmos. It's a story not of burning or exploding or growing, but of slowly, quietly, inevitably fading away. And that story stretches across timescales so long that the current age of the universe is barely a chapter. When a brown dwarf first forms, it's actually quite luminous. A young brown dwarf, fresh from the gravitational collapse of its parent cloud, can glow with a surface temperature of 2,500 to 3,000 Kelvin. That's not as hot as the sun, whose surface temperature is about 5,500 Kelvin, but it's still genuinely hot. Hot enough to glow a deep red. Hot enough that if you were close enough, you could see it with your eyes. A young, massive brown dwarf can be nearly as bright as the faintest red dwarf stars. In the first few million years of its life, distinguishing a young brown dwarf from a young low-mass star can be genuinely difficult because their luminosities and temperatures overlap. But here's the difference. The red dwarf star will maintain that brightness. It has sustained hydrogen fusion in its core, producing a steady stream of energy that keeps its surface hot and luminous for trillions of years. The brown dwarf will not maintain it. Without sustained fusion, without an internal engine generating new energy, the brown dwarf has only one source of luminosity. The heat left over from its formation, from the gravitational contraction that created it, and from the brief period of deuterium burning if it was massive enough for that. This residual heat is all it will ever have, and it's radiating that heat away into space, slowly but constantly, every moment of its existence. The cooling process is relentless. A brown dwarf doesn't cool suddenly. It doesn't flicker out like a candle being blown out. Instead, it fades gradually over immense stretches of time. In its first 100 million years or so, the cooling is relatively rapid. The surface temperature drops noticeably. The luminosity decreases. The object shifts from a reddish glow to a deeper, duller red. Over the next few 100 million years, the cooling continues but slows down. The brown dwarf is radiating less energy per second because its surface is cooler, which means the remaining heat is lost more slowly. It's like a hot coal cooling in the night air. At first, it cools quickly because the temperature difference between the coal and its surroundings is large. But as the coal approaches ambient temperature, the cooling slows because there's less of a temperature gradient driving the heat loss. After 1 billion years, a brown dwarf that started at 2500 Kelvin might have cooled to around 1500 Kelvin. After several billion years, it might be down to 1000 Kelvin or less. After 10 billion years, which is roughly the current age of the Milky Way's disk, many brown dwarfs have cooled to just a few hundred Kelvin. Some of the oldest brown dwarfs in the galaxy, those that formed in the earliest epochs of galactic history, have been cooling for over 10 billion years. Their surface temperatures have dropped below 500 Kelvin. Some have dropped below 300 Kelvin. These ancient brown dwarfs are among the coldest freestanding objects in the universe. They emit almost exclusively in the infrared, at wavelengths far beyond what human eyes can detect. They are, for all practical purposes, invisible. Dark objects drifting through the galaxy, detectable only with the most sensitive infrared instruments. This cooling trajectory has a profound implication. A brown dwarf's appearance changes dramatically over time. A young brown dwarf might be classified as an M or L dwarf based on its spectrum, with a surface hot enough for metal oxide and metal hydride features. As it cools, it transitions to a T dwarf, with methane dominating its spectrum. Cool further, and it becomes a Y dwarf, with water vapor and ammonia features. And if it cools long enough, billions upon billions of years, it would eventually approach the temperature of the cosmic microwave background radiation, about 2.7 Kelvin, the faint afterglow of the Big Bang. At that point, the brown dwarf would be nearly impossible to detect by any means. It would be just slightly warmer than the void of space itself. A dark, cold, Jupiter-sized object floating silently through the galaxy, carrying dozens of Jupiter masses worth of hydrogen and helium that it could never ignite. The universe isn't old enough for any brown dwarf to have cooled that far yet. Even the Kiwi oldest brown dwarfs are still a few hundred Kelvin at minimum. But given enough time, trillions of years, every brown dwarf in the universe will approach this final state. Objects with no light of their own, no internal energy source, no warmth, no glow. Just mass. Silent, cold, drifting through an equally cold and dark universe. This future is almost incomprehensibly distant. The universe is currently about 13.8 billion years old. For a brown dwarf to cool to near absolute zero would take trillions of years. By that time, most stars in the universe will have exhausted their fuel and died. The only stars still shining will be the smallest red dwarfs, those miserly nuclear furnaces that burn hydrogen so slowly they can last for 10 trillion years or more. Eventually, even those will die. And in the final epoch of the universe, when the last red dwarf sputters out and all that remains are stellar remnants, black holes, and the expanding void, the brown dwarfs will still be there. Cold and dark, yes, but still intact. Still held together by gravity and electron degeneracy pressure. Unchanged in structure, if not in temperature. Among the most enduring objects in the cosmos. Outlasting everything that once outshone them. Now let's step back and talk about how we got here. How did astronomers come to understand that brown dwarfs exist? Because the history of their discovery is a story about theoretical prediction running decades ahead of observational confirmation. It's a reminder that sometimes scientists can calculate what should exist in the universe long before they build the instruments needed to find it. The theoretical groundwork was laid in the early 1960s. In 1962 and 1963, the astronomer Shiv Kumar, working at the University of Virginia, published a series of papers in which he calculated the minimum mass required for a collapsing gas cloud to achieve hydrogen fusion in its core. His calculations showed that below a certain mass, roughly 0.07 to 0.09 solar masses, depending on the assumptions, the core would become degenerate before reaching fusion temperatures. He called these hypothetical objects black dwarfs, a term that didn't stick because it was later adopted for a different concept. But the prediction was clear. There should be objects out there that formed like stars, but weren't massive enough to shine like stars, objects that were substellar. The term brown dwarf was coined in 1975 by the American astronomer Jill Tarter. She chose brown, not because these objects are literally brown, they aren't, but because she wanted a color that fell outside the normal stellar color sequence. Stars are classified by color: blue for hot, white for medium, yellow for our sun, orange for cooler, and red for the coolest true stars. Tarter wanted a term that conveyed something beyond the red end of the stellar sequence. Brown, she reasoned, was a color that didn't correspond to any thermal emission spectrum. It was a non-stellar color for a non-stellar object. The name stuck, even though astronomers now know that brown dwarfs actually appear deep red or magenta when young and hot, and would appear dark purple or essentially black to human eyes when old and cool. They're never actually brown, but the name has endured for over 50 years now and is firmly embedded in the astronomical vocabulary. After Kumar's prediction, astronomers began searching for brown dwarfs, but the technology of the 1960s and 70s wasn't up to the task. Brown dwarfs are dim. They emit primarily in the infrared, and infrared astronomy was still in its infancy. The detectors available at the time were too insensitive, too noisy, and too limited in wavelength coverage to detect faint substellar objects. Decade after decade, searches came up empty. Candidates were proposed and then ruled out. There were false starts and misidentifications. Objects that seemed too dim to be stars turned out to be stars after all, just very distant or heavily obscured by dust. The search for brown dwarfs became one of the longest-running pursuits in observational astronomy. Everyone was confident they existed. The physics demanded it, but nobody could find one. The breakthrough finally came in 1995. In that single remarkable year, two separate teams independently confirmed the first brown dwarfs. The first was Tidey 1, a brown dwarf in the Pleiades star cluster, confirmed by a team led by Rafael Rebolo and Maria Rosa Zapatero Osorio at the Instituto de Astrofísica de Canarias in Spain. Its mass was estimated at about 55 Jupiter masses, placing it firmly in the brown dwarf regime. The detection of lithium in its spectrum was critical. As we discussed, lithium is destroyed in objects that sustain hydrogen fusion, so its presence confirmed that TIDA-1 had never achieved sustained nuclear burning. The second, and arguably more famous confirmation, was Gliese 229b. This object was discovered by a team led by Tadashi Nakajima and Ben Oppenheimer at the California Institute of Technology. Gliese 229b was found orbiting a nearby red dwarf star, Gliese 229a, at a distance of about 19 light-years from Earth. What made this discovery so convincing was the spectrum. Gliese 229b showed clear, unmistakable methane absorption features. No star has methane in its atmosphere. Methane only survives at temperatures well below the coolest star. The presence of methane was definitive proof that this object was substellar. Its surface temperature was estimated at about 950 Kelvin, and its mass at roughly 30 to 40 Jupiter masses. After more than 30 years of searching, brown dwarfs were finally confirmed to be real. The years following 1995 saw an explosion of discoveries. Infrared sky surveys like the 2-micron All-Sky Survey and the Sloan Digital Sky Survey revealed hundreds of brown dwarfs. The spectral types L and T were formally established to classify these new objects. Each year brought new discoveries, new record holders for coolest temperature, new companions to nearby stars, new free-floating brown dwarfs wandering through interstellar space. The WISE mission, launched in 2009, pushed even further into the infrared and discovered dozens of white dwarfs, the coldest spectral class. Some of these objects turned out to be startlingly close to Earth, hiding in our cosmic backyard, invisible to every previous generation of telescopes. The galaxy, it turned out, was filled with brown dwarfs hiding in plain sight. And this brings us to one of the most important things brown dwarfs teach us. They're common. Far more common than anyone initially expected. Current estimates suggest that there might be roughly one brown dwarf for every 6 stars in the Milky Way. Some estimates go even higher, suggesting brown dwarfs might be nearly as numerous as stars themselves. If the Milky Way contains around 200 to 400 billion stars, it might contain 50 billion to 100 billion brown dwarfs, possibly even more. Tens of billions of objects scattered throughout the galaxy, each one a Jupiter-sized ball of hydrogen and helium that almost became a star but didn't. They represent a significant fraction of the galaxy's total population of collapsed objects. And yet, until 30 years ago, we didn't even know they existed for certain. This abundance tells us something fundamental about how star formation works. When a molecular cloud fragments and collapses, it doesn't produce only objects above the hydrogen fusion threshold. It produces a whole range of masses. Some fragments gather enough mass to become massive, luminous stars. Some gather just enough to become the smallest red dwarfs, and some fall short, ending up as brown dwarfs. The distribution of masses that comes out of a star-forming region is called the initial mass function. It describes how many objects of each mass are produced. The initial mass function has been studied extensively, and it shows a clear pattern. Most of the objects produced by star formation are low mass. There are far more small stars than large ones. The most common stars in the galaxy are the smallest red dwarfs. Massive, luminous stars like the Sun or larger are actually quite rare. And the initial mass function doesn't stop at the hydrogen fusion boundary. It continues smoothly downward into the brown dwarf regime. The same physical process that makes lots of small stars also makes lots of brown dwarfs. There's no gap, no discontinuity at the fusion threshold. Nature doesn't know or care about our categories. It just produces objects across a continuous range of masses, and some of those objects happen to fall above the fusion line, and some fall below it. This continuity is strong evidence that brown dwarfs form the same way as stars. If brown dwarfs formed through a fundamentally different process, you might expect a gap or a change in the mass distribution at the stellar boundary. But there's no gap. The distribution flows smoothly from the most massive stars down through red dwarfs, through brown dwarfs, and likely continues into the planetary mass regime for objects formed through cloud collapse. This smooth distribution is one of the strongest arguments that brown dwarfs are the low-mass tail of the star formation process, not a separate class of objects that forms through a different mechanism. Brown dwarfs also teach us about the physics of very cool atmospheres. No planet in our solar system has exactly the same conditions as a brown dwarf. Jupiter is similar in some ways, having a hydrogen and helium atmosphere with methane and ammonia. But Jupiter is far less massive and far cooler than most brown dwarfs. Brown dwarfs bridge the gap between stellar atmospheres and planetary atmospheres. They allow astronomers to study atmospheric physics under conditions that can't be reproduced in any laboratory on Earth. Understanding how clouds form and dissipate in brown dwarf atmospheres, how chemical species are distributed at different altitudes, how atmospheric dynamics work in the absence of stellar irradiation, all of this feeds directly into our understanding of giant exoplanet atmospheres. Brown dwarfs serve as natural laboratories for atmospheric science. Now, let me return to where we started and address the term that hangs over everything we've discussed tonight. Failed star. You hear it everywhere. In textbooks, in documentaries, in popular science articles. Brown dwarfs are failed stars. The term is catchy, it's dramatic, and it's deeply misleading. The word failed implies that the brown dwarf tried to become a star and couldn't, that it attempted something and fell short due to some deficiency or error, that it's broken, incomplete, defective in some way. But none of that is true. A brown dwarf didn't try to become anything. It didn't have an intention or a goal. It simply followed the laws of physics. Gravity compressed a cloud of gas. The cloud heated up. Electron degeneracy pressure halted the compression before hydrogen fusion temperatures were reached. Every step happened exactly as physics requires. There was no failure at any point. The brown dwarf did exactly what the laws of nature dictated. It's not a broken star any more than a hill is a failed mountain. The word failed also implies that being a star is the correct outcome, and that anything else is a mistake. But the universe produces both stars and brown dwarfs in enormous quantities. Becoming a brown dwarf is just as natural an outcome as becoming a star. Calling brown dwarfs failed stars is like calling silver a failed gold. They're different outcomes of the same fundamental processes, each valid, each with its own properties and its own role in the cosmos. What brown dwarfs really are, stripped of the misleading language, is this. They're a natural product of gravitational collapse. They occupy a specific region of mass space between the most massive planets and the least massive stars. They form the same way stars do. They're made of the same material, but they lack the mass to cross the threshold into sustained hydrogen fusion. This doesn't make them failures. It makes them a distinct class of objects with their own unique properties, their own atmospheric chemistry, their own evolutionary trajectories, and their own place in the cosmic hierarchy. If anything, brown dwarfs remind us that the universe is richer than a simple binary of planets and stars would suggest. The cosmos makes a continuum. From the smallest rocky bodies to the largest supergiant stars, there's a spectrum of objects occupying every possible niche. Brown dwarfs fill one of the most important niches, the gap between planetary masses and stellar masses. Nature doesn't skip. It fills every available space, and brown dwarfs are how it fills this one. Consider how many brown dwarfs are out there right now. Tens of billions in our galaxy alone. Probably hundreds of billions or trillions across the observable universe. Each one a Jupiter-sized object carrying dozens of Jupiter masses worth of hydrogen and helium. Each one slowly cooling over billions of years, radiating away the heat of its formation into the void. Each one a physical record of a gravitational collapse that fell just short of the threshold for sustained fusion. They're among the most numerous collapsed objects in the cosmos, and they were completely unknown to science until a single generation ago. Some of these brown dwarfs have companions. They orbit stars. They orbit other brown dwarfs. Some exist in binary systems where two brown dwarfs orbit each other, locked in a gravitational dance around their common center of mass. Neither one a star, both slowly cooling together through the ages. Some brown dwarfs have been found with disks of dust and gas around them. Disks that might eventually form planets. A brown dwarf with its own planetary system. Worlds orbiting a world that isn't quite a star. It's an idea that stretches the imagination, but it's physically plausible, and there's growing evidence that it happens. And some brown dwarfs are alone, free floating through interstellar space, not bound to any star, not orbiting anything, just drifting. These solitary brown dwarfs are perhaps the most evocative objects in the story. Imagine one of them. A ball of hydrogen and helium, roughly the size of Jupiter, perhaps 50 times Jupiter's mass, formed billions of years ago in a molecular cloud that has long since dispersed. It might have formed alongside stars that are now scattered across the galaxy, siblings it will never see again. It has been cooling for billions of years. Its surface temperature might be a few hundred Kelvin, barely warm. It glows faintly in the infrared, invisible to any eye. It drifts through the galaxy at tens of kilometers per second, following an orbit around the galactic center that takes hundreds of millions of years to complete. It passes through clouds of gas and dust. It drifts past other stars, other planetary systems, other brown dwarfs, never interacting, never stopping, never changing, just cooling, just drifting, just being. It carries within it enough hydrogen to power a star for billions of years, but it can never use that fuel. The temperature in its core, though still millions of degrees, isn't enough. Electron degeneracy pressure holds the core rigid, preventing further compression, preventing the temperatures from ever reaching the threshold. The fuel is there. The conditions are not. And they never will be. Not in a billion years. Not in a trillion. Not ever. Unless some catastrophic event, a collision with another object massive enough to push it over the threshold, intervenes. And in the vast emptiness between stars, such collisions are so rare as to be essentially impossible. This is the quiet fate of a brown dwarf. Not the dramatic death of a massive star that explodes as a supernova, scattering its elements across light years of space. Not the steady, patient burning of a sun-like star that sustains life on its planets for billions of years. Not the slow cooling of a white dwarf, the remnant of a star that already lived its full life. A brown dwarf never had that life. It was born into cooling. Its entire existence, from formation to the ultimate darkness, is a single, long exhalation of heat, a slow return to the ambient temperature of the cosmos. And yet there's something magnificent about that. Because brown dwarfs endure, stars burn out, massive stars explode after millions of years, sun-like stars exhaust their fuel after billions. Even the longest-lived red dwarfs will eventually die after trillions of years. But a brown dwarf, supported by electron degeneracy pressure, doesn't burn out because it was never truly burning. It just cools. And cooling takes a very, very long time. Long after the last star in the universe has died, long after the galaxies have gone dark, brown dwarfs will still be there. Cold and invisible, yes, but still intact. Still themselves. Among the last coherent structures in the universe, winding down toward maximum entropy. So what is a brown dwarf? It's not a failed star. It's a substellar object that formed through the same gravitational collapse that creates stars but didn't accumulate enough mass to sustain hydrogen fusion. It occupies a mass range between about 13 and 80 Jupiter masses. It may briefly fuse deuterium, but this is temporary and doesn't establish true stellar equilibrium. Its core is supported by electron degeneracy pressure rather than by radiation from nuclear fusion. It cools over billions of years, fading from a dim reddish glow through progressively cooler spectral types until it eventually becomes a cold, dark object drifting through space. And why did it never become a star? Not because it failed, not because something went wrong, but because the laws of physics set a threshold, a minimum mass required for sustained hydrogen fusion, and the brown dwarf fell below that threshold. It lacked a few Jupiter masses worth of material, that's all. A few Jupiter masses, gathered or not gathered from a primordial cloud of gas billions of years ago, determined whether an object would shine for trillions of years or slowly fade into darkness. The difference between a star and a brown dwarf is not a difference in kind. It's a difference in degree. A difference measured in a few percent of a solar mass. A cosmic coin flip that happened billions of years ago and cannot be undone. The next time you look up at the night sky, remember that for every star you can see, there are brown dwarfs out there that you can't, hidden in the darkness, invisible to your eyes, slowly cooling, carrying within them the fuel for stars that will never ignite. They're not failures. They're not mistakes. They're part of the universe's full spectrum of objects, occupying a place that physics carved out between planets and stars. And in their quiet way, in their slow fading, in their patient endurance across cosmic time, they're as remarkable as anything that shines.